Hello everyone, and thanks for joining this webinar on optical filters. My name is Marc-André Laliberté. I am a product line manager at TeraXion and covering pretty much everything related to optical communications. So real quick, I'll just cover what TeraXion does. We have multiple expertise. The first one, fiber Bragg ratings, is the topic of today. So we can do pretty much what we want with fiber Bragg ratings. We've done this since the beginning of the company. Then we also do narrow linewidth DFB semiconductor lasers. We designed our own chip that we put in our butterfly in our own laser module. We have experience with low noise electronics. That's part of that laser, by the way. Then we have experience in silicon photonics. We've done a lot of different projects that needed some those kinds of components. And of course, we have experience in packaging all of this into these neat golden boxes. So at TeraXion, we can design, we can integrate, we can test, and of course, we produce. We have product lines. We also acquired Exelos recently. So with Exelos, that's new expertise that is added. They've been dealing with many semiconductor materials to work in the visible range, but also in the near infrared. They developed SLED and laser diode modules, and they produced quite a lot of those. They can do drive and control electronics to drive those lasers. A very excellent expertise in integrated optical modules. They can place a lot of those SLED modules inside one butterfly, like here. And they also worked with a third-party manufacturer to develop a system for automated packaging so that they can produce thousands of those units. So in terms of products that we can supply, we have a bunch related to SLEDs, SLED modules, integrated optical modules, SOAs, the electronics to drive all of this, and also benchtop broadband light sources that can be pretty useful. We supplied narrow linewidth lasers for many years. This one is the new LXM, by the way. Very narrow linewidth, the linewidth of a fiber laser, but with a DFB. We also have visible laser diodes and ultra-fast lasers, the Vinci that we launched last week. We also have fiber laser components for high power and ultra-fast lasers. There are kind of optical filters, Raman scattering, ASE filtering. We have pulse stretchers, wavelength lockers, reflectors, and couplers as well. And here you have my products, optical communication and sensing components, optical filters that we will be talking about very soon. And also chromatic dispersion compensators and chromatic dispersion emulators. So this is the agenda. I'll present the basics of FBGs to make sure you understand what you would be dealing with if you don't already know. I'll show you real examples for different types of FBGs. Then the next section will give you an overview of the knobs we can turn and give you a feel of what you can expect. And then we'll see the packaging options as well as typical use cases. So throughout the webinar, we'll collect live questions and we'll answer as many as possible. To begin with, what are fiber Bragg gratings? What we do is that we will modulate the refractive index on a portion of the fiber to create an FBG that is in fact a mirror reflecting certain wavelength while the remaining is transmitted. So yes, an optical fiber transmits light. So we'll just select what will be reflected. There are different types of FBGs. It can be a uniform FBG like this one here, where we'll just select a very well-defined portion of the spectrum that will be reflected in the fiber. We can do tilted FBG here. It's the same concept, but instead the reflection will be in the cladding. This can be very useful to prevent using an isolator when cascading filters, for example. And then we have chirped FBGs. So the period between the high reflective index and the low reflective index is changing along the fiber. So the goal here is to reflect wavelength, but not at the same time. So you'll have photon reflected earlier in the FBG, and some will be reflected deeper inside the FBGs. So that will create a delay that can be used to stretch a pulse or compress it. So we use this for dispersion compensators, dispersion emulators, pulse stretchers, and some special filters for fiber lasers. But this will not be covered in this webinar. There is more than one way to make an FBG. The one presented here is to use extremely high resolution ultraviolet light that you pattern using a phase mask. Each phase mask is designed for a set of requirements. So as you send light, UV light to it, an interference pattern will be created on the fiber, creating areas of high and low refractive index. Over the years, we designed a lot of phase masks, so we have racks of it that can be reused, and that's the beauty of this technique, as it provides excellent repeatability for recurrent products for challenging applications. That being said, we can also write FBGs using femtosecond lasers. That's another technique we have available. There are many types of FBG profiles. There are many types of optical filters. What I'll be presenting here are the profiles where the FBG optical filters really shine. So this is where the technology is really appropriate and will give you the best performance you couldn't get otherwise. The first example is a narrow filter. This is where you want one single, very narrow reflective band. It's typically designed with the steep edges and flat top. This one is on the limit with 2 gigahertz at minus 3 dB. So it's way too narrow to do flat top. But starting at 4 or 5 gigahertz, you should have it pretty easily, along with higher reflectivity. You can see this one as a very high isolation. This is often what we're aiming for. This example is a bit wider than the previous one. You can see the flat top right here. It is also quite interesting because the isolation is really high. The side mode suppression ratio is down to minus 50 right next to the edge. For this one, it's 2 FBGs that were put together on a circulator. And just so you know, we can go even deeper than that now. Another nice example, quite a bit wider, but what is interesting is that we get a 60 dB isolation with one single FBG. In that case, we're not looking at the side mode suppression ratio next to the band, but instead the reflectivity. So it's really suppressing something really strongly, in that case at 99.9999% to get that 60 dB insertion loss in the transmission profile here. We are now looking at a wideband filter. That's another example where, yes, it is a large filter, nothing special there, but again, we made it highly reflective, like the previous example. In that case, one may just want to extract a specific portion of a larger spectrum. You send it back to a circulator, and then you can start doing other operations on it. Another really important use case of such large filters is to suppress Raman scattering for fiber lasers. In that case, we'll be using tilted FBGs. Here, yet another wider filter, but this one is asymmetric. This is something we can design on purpose to make sure we can achieve the steepest edge on one side, that case on the left side. This becomes very useful to separate, for example, two bands that are very close to each other. By focusing on one side only, we can also ensure the reflectivity is really maximized. Here I show another example of an asymmetric filter. In that case, turns out both sides are quite steep, but it's just to show you that if you have a laser with a sideband on each side, you can see that you can position that steep edge exactly between the two bands so that only one band is collected with a circulator, for example, and the rest is suppressed, in that case, down to minus 35 dB. Here we see an example of a Gaussian filter. Again, this one is very narrow, but regardless of the bandwidth, we can shape the filter profile the way we want, basically. You can see on the left side different high-order Gaussian functions that will give you different super Gaussian profiles depending on what you want to do with that filter. Here we see an ultra-narrow filter. First thing to notice is the y-axis that is now in transmission. So we're talking about bandpass filters. At the middle, you will have this band that will transmit light, whereas on each side you have these large reflective bands with very high isolation. The profile of the band is Lorentzian. This one is rather large for an ultra-narrow filter. It's 500 megahertz. This one is 35 megahertz, so it's the other extreme. These filters find many uses. I'll talk about this later, but if you want to look at publications, there is this rather old paper that we published in 2010. Otherwise, if you search on the web for phase-shifted FBG TeraXion, you'll find many other articles. Now, these filters are leveraging our expertise on multi-channel dispersion compensators for the telecom/datacom market. Here we just focused on the reflectivity profile. So all these bands can span across a very large range of frequency, like the whole C-band. And what's fun with using an FBG like this is that you have much more freedom in terms of design and what you can do with it compared to, let's say, a Fabry-Perot Etalon. So you can play with the reflectivity, the type of band profile, the isolation, many knobs we can play with. Here's another one where the shape is more Gaussian instead, whereas the other one was Lorentzian. So we can play around and change the FSR and change the profile that way. In the next section, I'll cover a bunch of various topics that are quite important to make sure we properly understand each other, to make sure we set the expectations straight, to make sure we optimize what you'll get from the FBG, as there are quite a few knobs that we can play with. First here, I'm just trying to point out that reflection, isolation, and insertion loss are interrelated. As we define the spec, details will be very important. For example, if you take the percentage of reflectivity, you might say, okay, that's directly the insertion loss that I'll get. But if there is a circulator, you may want to consider both the insertion loss from the reflectivity and the insertion loss of the circulator itself. Another one, when we talk about isolation, in general, we refer to the ratio between what's reflected and what's transmitted. First off, there are many names for this: side mode suppression ratio, side peak suppression ratio, out of band isolation, extension ratio, and so on. But most importantly, we need to understand where that isolation must be and what are the signals at play. We'll just need to clarify this very well together. The next two slides will try to demonstrate a bit what I was trying to say. What is the extinction ratio between the signal in red that we want to suppress as much as possible and the target signal in green here? We are looking at the transmission spectrum in blue. So we'll reflect that signal here to more than 99.9999%, which in transmission means more than 60 dB of insertion loss. The target on the other side is only reflected to minus 40 dB, so the insertion loss in the end is minimal. So yeah, here in that case, the extinction ratio on the transmitted signal in green will be 60 dB. The extinction ratio on the reflected signal is approximately 40 dB with respect to the signal in green. Here we just focus on the reflection profile instead, where we want to collect the target in green here and transmit the red signal, regardless of what's happening with this one. In that case, the extinction ratio is between the reflectivity on top and the level of the sine modes on each side. So that's roughly minus 35 on this sine mode versus approximately minus 2. That's an example from the circulator, the insertion loss of the circulator. So in the end, that's more than 35 dB of extinction ratio between these two signals. This slide is also about isolation and what we can achieve. You see here that this is a statistical process, obviously. So once we get a new design, we never did that filter, so we'll usually spec it at more than 20 dB. Once we get it in production, then we'll be able to tweak, to optimize, and then we'll reach that ultimate value that we know we can achieve in the future if you repeat that filter. Of course, for some design, we'll know upfront that it will be easier to have more isolation or less. This is dependent on the level of reflectivity of the FBG profile itself. Then there's also a matter of how you define isolation, where you define it. So at which distance from the central wavelength we'll calculate this. Depending on your application, you may require a very specific value right next to the edge, for example. And sometimes whatever needs to be isolated is further away. In that case, you can look at the mean value or the absolute value over a region, depending, again, if you're looking, for example, at limiting white noise everywhere, or just removing something very specific at a specific distance. Here we look at the edges of the FBG profile and how steep it can be when required. Our default value will be 5 dB per gigahertz. Very common is the need to separate bands less than 10 gigahertz apart with the highest isolation possible, so it has to be very steep. So this example obviously beats the 5 dB per gigahertz. This is a very steep filter where we got 20 dB of isolation over 1.6 gigahertz. So that is a steepness of 15.6 dB per gigahertz. So not all designs can reach that level, obviously, but this is a good example of an asymmetric profile where one side we just didn't care too much. We made sure that the filter was as wide as it could be, and we focused the whole design on that left edge here. Here I'm presenting a concept briefly mentioned earlier. It's the fact that at very low bandwidth, once you are close to that 2 gigahertz mark, you cannot get a perfect reflectivity. In that case, that roughly 50%. Of course, it's a statistical process again. So sometimes it will be a little less, sometimes it will be a bit better. But once you hit that 5 gigahertz mark, you can get that 99% and more reflectivity. This is an example in the C band, but the same concept will apply at other wavelengths. For the center wavelength, and the optical bandwidth. We also have typical specifications. Again, highly dependent on the actual design. Athermal packages can affect the wavelength as well, the tolerances. Sometimes it allows us to fine tune and lock the center wavelength better. Sometimes it's more difficult. For example, an FBG in SMF fiber will always have better tolerances, whereas PM fiber can be a little more tricky sometimes because of the tension applied through the athermal packages. Note that these numbers, again, are related to athermal packages. These are measured from -5 degrees Celsius to 70 degrees Celsius. On the optical bandwidth, the typical tolerance will be plus or minus 5%. So just to have a bit more feeling about this number, most of the designs, 70%, will be within plus or minus 5%. If you take 10 plus or minus 10%, that's 90% of the designs that will fall within. Of course, when considering very, very narrow filters, the percentage is not the same. We're mostly looking at plus or minus 1 gigahertz. And for ultra narrow band filters, we're talking plus or minus 20 to 25%. In general, it's important to note that I've been talking about historical data, but in recent years, we implemented new analyzers where the resolution is much better. In some cases, the tolerances are actually better than we thought they were, specifically on the isolation. And to finish that section, I want to present an option for some applications where low dispersion filters are important. You don't want to create any delay on your pulses, side pulses, while filtering it. So this option will give you a group delay typically of plus or minus 5 picoseconds in variation. So you can see it's very flat. This example is 6 picoseconds peak to peak. And on the left side, it's the same filter where we're showing multiple iteration of different filters of the same design to show that this is a repeatable process. Like I said earlier, once we start producing a filter, we establish the recipe, and then we can reproduce it the exact same way over and over. Packaging is a very important part. You have the FBG where we tailored everything, but then you are expecting functionalities beyond the spectral filtering itself. And this is where the packaging comes in and gives you extra benefits. You don't see here all of the exact modules that we have, but it's the 3 different types that we offer: recoated, athermal, and tunable. Once the FBG is written, we recode it, and then we can further protect it with a loose tube and sometimes with a rigid tube, as you can see here. Some people will ask for the bare fiber sometimes. We don't recommend it, obviously, but it's a possibility when it's a hard requirement. Regarding central wavelength stability, it will be that of the fiber used. In the case of the SM fiber, the SMF28, it's 10 picometer per degree Celsius. So in the end, if your tolerances are respected and you can deal with such a simple package, that's the most economical choice. Now, if you need very stable FBG optical filters that will not drift with temperature, but still within a passive and simple package, you have the athermal optical filters. The design of the internal tubes and the selected material compensate for the thermal expansion of the fiber that would otherwise shift the central wavelength. We have different packages that will protect the FBG and thermal assembly, accounting for the length of the FBG, the number of FBGs, the type of fiber, and the reflection and transmission port as applicable. So again, this is an example for single mold fiber. The stability in that case would improve to less than 0.7 picometer per degree Celsius. And finally, we have the tunable modules. Those are active modules, thermally controlled over a range of plus or minus 30 gigahertz with 2 picometer resolution and a stability of roughly 40 megahertz peak to peak over 24 hours. And some people improve this even further to 10 megahertz using a feedback loop. You can see different modules with reflection and transmission ports, circulator or not, for SM fiber and PM fiber. So this is for high performance applications and for R&D and benchmarking purposes. In R&D mode, for example, you will want to tune your filter, move that steep edge or sharp notch precisely, making sure you properly define your own tolerances and understand your system the best you can. Then you may tighten your specifications or relax it to the point where the thermal package might suit your needs. And now for the last section, we'll look at the strategies and applications, how people use the filters and the different schemes that we propose. It's not 100% exhaustive, of course. There are so many ways you can play with an FBG in your optical setup, but we'll look at the most important ones. The first example is the most typical one, where you want to isolate a signal from any interference. Including just the noise on each side of your band. So you will collect your signal with a circulator, so it will be reflected here. That's assuming you have the insertion loss budget to do so. You will often want to maximize the isolation to optimize your signal to noise ratio. Depending on the isolation, you can put more of those FBGs in series to achieve the max extension ratio on each side. This is useful for BOTDR, for DVQKD as well, where any interference will mess it up greatly. BOTDR will require very sharp edges, so you want to move that edge to just pick up the brilliant signal, one sideband 11 gigahertz aside, and avoid your modulated laser. DVQKD will require very often a narrow bandwidth with very high isolation to clean everything going into the QKD channel. This one is the same concept where you extract a signal with very high isolation, but instead of repeating one FBG, one circulator, we use a 4-port circulator with 2 FBGs on it. So with one module, you maximize the isolation you have. It's a matter of dimension. We can do this with thermal and tunable packages. This is very useful for microwave photonics, radio frequencies over fiber applications, where they always push for the maximum extinction ratios, especially in aerospace and the defense industry, where they have the most stringent requirements. This scheme is gaining a lot of traction. Here you want to suppress something really strongly, for example, a pump laser, and the rest will be transmitted. I showed earlier that you can have very low insertion loss this way. So obviously, low insertion loss, high isolation, if you suppress very strongly, this is gold for quantum optics. We've had cases of suppressing the pump laser for quantum dot emissions, for SPDC and single harmonic generation, where you don't want single photons from your pump. So it has to be very clean. Otherwise, with a circulator, it can also be used to separate a carrier from sidebands, for example. Then from a simpler scheme, this is where you can get funky. So 60 dB is usually a step to reach 120, which comes up a lot. So here you have 60 dB per FBG, and you put them in series with an isolator in between to make sure you're not creating a cavity, which could induce nonlinear effects. This is very hard to quantify. That depends on the signal, on the power that you put through these FBGs. Another example is to use instead a standard DWDM filter when this is applicable, of course. This will give you a bit of insertion loss, but it acts as both a filter and a circulator. So you have the FBG that will push further the extension ratio, and you can still retrieve a reflected signal even though the isolation may not be as good. And finally, an example with the ultra narrowband notch filters. You can use it directly, just the FBG. You may want to shape a signal. You have a source that is a bit too wide or that may be unstable. So a sharp notch along with the tunable platform will stabilize the shape and intensity. Another use case is to retrieve a sideband from the changing modulation of a laser. So you actively tune the filter to find that band. And sharp notches can also be used to modulate the intensity of a laser. So as it shifts along the filter's edge, the intensity will quickly change. So to conclude, those were guidelines, some overview so that you get the idea of what we're doing. But once we'll get into a discussion, we'll likely go deeper. We have design sheets, we have a product guide. In fact, this webinar is an extract. We have a user requirement document that we'll fill out with you. Just with this slide, you can already prepare for a discussion. And this is to really clearly understand your challenges, your needs, your expectations. You know your application. The goal is to retrieve as many details as possible and identify faster what will be the best solution that we can offer. On our side, we have the tools, we have the expertise, we have the experience, and we'll just propose what we think is best for you. You need to see us as an extension of your team. We will work together, get excited, find a solution, and it will work.